So this is the video on the differential geometry and a very core concept about the light derivative as the commutator. So this is a very important topic for the in a differential geometry and also for the relativity, which is specifically the general relativity, where we discuss about the curvature and the space time curvature, how to the parallel transport on the curved surfaces and all that stuff. That's why it's very important. So in this particular video, I'm going to prove a very important result, and the result is that the light derivative acts when on the y is equals to the commutator of the vector fields between x and y. So if you have studied the differential geometry, you must have encountered this particular very important result, and it's a also very famous result. Light derivative when you do the light derivative of the y, it is equals to the commutator relationship between the x and y. And you also, when you have studied differential geometry, you also know that the commutator of x and y generates another vector field, the third vector field, you can say. So taking the commutator between the two vector field x and y, there is another vector field. That's why we define the commutator, and this commutator is equals to the light derivative of the y here. So we are going to prove this particular result. This is very important result. So for this, you have to know some of the basics. Light derivative acts on the different things. So the basic things are, first, when the light derivative acts on any function f, how you can write this? So you write this as x of nu del f by del x of mu. So this is how you write when the light derivative acts on the any function f, and this is also a very important result. You have to remember, we will directly use this result while deriving this particular result of the commutator relationship. And here you have to be careful with the indices. So here this is mu. Let me write the indices. Okay, so this is x of mu and del f divided by del x of mu. So this is how we define first result. Now move to a second result, which is what will happen if this light derivative acts on a coordinate basis. Like one of the bases that we encounter in the physics is I cap, j cap and k cap, but in the manifolds we have to generalize this particular thing and we denote it with the del of mu. You will study this in the topology, especially when you discuss about the tangent vectors. We will discuss that how we can write out the vector fields x as x mu divided by del x of mu, and this is the coordinate basis for our vector field x, and this x of mu is one of the components. So the analogy of this particular x can be viewed as the velocity vector v is equals to vx I cap. So just like here, the I cap plays the role of the basis vector, this particular del of mu is playing that role, and this x of mu is the component of this vector field x, and this is exactly what this vx is one of the component of our this vector v. Okay, but what happened is that we are defining here in the manifolds, that's why we have to generalize something, and that's why it's important to know about these stuff. So what will happen if this light derivative acts on a coordinate basis? So you have to remember this result. It's a very important result, and directly we are going to use it, and it is equals to the negative of del divided by x, and here del divided by x. And here you have to be careful with the indices that I'm going to write. So this is nu, this is mu, and this is mu. So this is one of the most important result that you have to remember, that this particular result, when you act the light derivative on a coordinate basis mu, it is equals to the negative of minus del x nu divided by del x mu into del nu. You can generally prove this, but proof is quite long, so I will not going to derive this here, but in the next video for sure I'm going to derive these two results we are going to derive. Okay, both of these two results. In this particular video, our main focus is the derivation. Now we are going to do the real thing, which is what will happen if I derive, you can say that act this particular on any vector field y. This is looking like x. Okay, this is okay y. So what will okay y. So how will this happens? So to know this, you have to know a very important formula, which is also a very basic formula, and you will see in the every topology and the vector field notes that how can we write our any vector field y. So any vector field y can be written as y, here mu del I by del x mu. So this is one of the very important result, that how to write the vector field y as y of mu, where y of mu is the component of this particular vector field. So just like this, we are going to write this here. So this particular result can be also written as L of x y of mu del by del x of mu. Okay, so now Lx of y of mu. One important thing also, that the short form of this particular thing, which is the coordinate basis, is here del and here mu. So this is a short form of this. So we are going to act it. So you know how it's gonna act. The lie derivative follows the linearity rule and all of the rules that you have studied in the section of the vector fields and lie derivative. You can also see that particular thing in the David Tonks lecture note, a very excellent notes. Okay, so it will act like this, that first of all it will act on Lx, then y of mu, then del of mu here is will be, and then plus y of mu and y of mu, and now this Lx will act on this mu. So it's just like the basic differentiation rule that we have studied in the class, that what is the differentiation of some of the functions which are in the product. First of all you differentiate the first, then you keep the second as constant, and then you differentiate the second. So this is just an analogy. Here there's a very different thing occurring, but this is just an analogy of, suppose that you want to do the sin x and cos x. First of all you do the derivative of sin x, put cos x same as, just like here I have do these particular line derivative acts on this particular y, not on this, and on second it acts on this, not on this. Okay, this is a basic rule that you have to know. Now the main game is the result that we have derived, that what will happen if this particular lie derivative acts on any arbitrary function f. We can write this as this. So here our f is y. So using that particular analogy, we can write this particular result as x of mu del by one minute, I have to choose the another superscript, because here I have chosen this mu, so I will now choose nu. So nu is more like a v. Okay, so v, and here del y mu divided by del x nu, and here del mu. So this is the first result that we have derived. Now plus this is our result. So this is like the lie derivative acting on a coordinate basis, and we have just written here the formula of this. You know, that's why I have said that it is very important. So now writing this as y of 1 minute, my y, okay, my writing is not that much perfect. Okay, again it's look like at 1 minute. Okay, y and then mu, and what will happen if this lie derivative acts on the del of mu? So it's like the formula that we have derived, it's negative of del, according to the formula, x of, so del x of, here you can see the formula del x of mu, but here we have chosen nu, so del x of nu divided by del x of mu, and here the another thing is del of nu, del of nu. So this is our thing. We have written this with the help of this particular formula. This formula is very important, you have to remember this. I have directly written the things that is written here in this particular formula. Okay, so now let me write it in a more clear way, that how we are going to write this. So this is equals to the x of nu is more like a v. Okay, you have to understand, and del of y of mu, this is mu, 1 minute, del y of mu divided by del x of nu del of mu plus y of mu, here it should be negative sign. Okay, I'm writing here the negative sign, and it will be del x of nu divided by del x of mu and del of nu. So this is our result, and this is equals to the Lie derivative acting on our y. See here, this is a very important thing I'm going to talk about. The commutator relationship that we have defined is exactly equals to this. If you don't believe, just see this. I guess I have derived the relationship. 1 minute. I guess I haven't derived that. Oh, I thought I had derived that. Okay, so you can generally see from yourself that when you will apply the commutator relationship between the x and y, commutator relationship between the 1 minute. Okay, so you can generally see that you can generally define the commutator relationship between x and y acting on function f, and this exactly looks like this. So what I'm going to do is that I'm going to substitute here the commutator relationship of x and y. X, y is equals to the commutator of x and y, and this is a very important result, and we have to prove this, and we have proved this. Okay, so this is a very important result. The fact is that you can check on yourself that how to do this, and if you don't know, I can just give you a direction of calculating the Lie derivative of x and y. So, and this is equals to the, let's choose it to be acting on a some function f, and let's see how it will be. So let me here give you the hint. You can calculate on yourself. The calculation is pretty much straightforward. So what you can do is that you can here write down x as x of mu, let's say, and del by del of, the formula will be quite lengthy. What I'm going to do is that you can do like acting x of f, then y, then plus x y of f. Okay, so this is the thing. Then what you can do is that you can, you know that how to, what's the formula of this particular x, how to represent this x. So the formula of your any vector field x is represented by x of mu and del by del x of mu. What you have to do is that you have to just put here the function f. So it means you can write this as x of mu del by del x mu, and here your function f, and here y. 1 minute, here f, here f, here f, and here it should be y. And the similar thing you can do for this particular second part, and here y. And the similar thing you can do for the, put x aside and do the same thing as y of nu here, and del f by del of y of 1 minute, del of x of nu. Okay, this is I'm giving you a hint. You can go this afterward and you can do all the calculations here, and you will be good to go, and you can generally prove that result. What you have to do now is that you can now generally write down this y thing, that how to write y. Then y is equals to the y of nu del by del of mu, and generally after writing this you can derive the result of the commutator relationship between the two vector fields and give me the direction. If you want, you can do that. Okay, it's fine. And now this is our video. We have discussed about the Lie derivative as the commutator relationship, and this is our relationship, and this is very important. You have to remember this, because of this you will encounter this in all of the differential geometry topics. Even when you discuss about other topics like the another advanced topics of integral curls, maybe it will be useful to define the Lie derivative, because Lie derivative is one of the core concepts of the differential geometry that arises, and if you are not doing this particular topic, then you're missing a lot of things. I mean a lot of things. So that's why you have to do this particular topic. Okay, so this was my video on the proving the commutator relationship between the Lie derivatives. Another video is going to be on more fascinating topics of the differential geometry. Maybe I guess we can discuss the topics like the one form and two form, the covector forms, and the curvature forms, the Riemannian curvature tensors, how to derive the Riemannian curvature tensors, and the differential forms, the exterior derivative. These are some of the important topics that are in my list, which I will discuss. So this is my video on the differential geometry first part. So thank you for watching my video.